So talk about the port multiplexing. So port is a kind of communication endpoint. So if you compare the figure, the node-to-node channel and also the end-to-end channel, so this is a, a link, two hosts, well, two stations, two hosts or two stations connected with a link, a node-to-node channel, and then you would have, on the host, you would see a MAC address and IP address. And the figure here shows the delay distribution, which is quite condensed, meaning the x is the delay and y is the percentage of the distribution, the delay distribution. So you will see most of the delay is quite concentrated, condensed here, so not much variation. However, in the end-to-end channel, you will see that the delay distribution is quite loose. It would be something like with this kind of distribution with a long tail, meaning that because it's multi-hops, it's multiple links concatenated together. So two hosts concatenated by a network, and the network could have many, along the path there could be links and routers, many links and many routers on the link on the path. So the delay distribution will be quite loose with possibly a long tail. So that's one characteristic we have. So people would say that if I'm two node connected by just one link, then what you see will be the left-hand side figure, and they are immediately connected. However, on the end host, at the transport layer, it's high in the transport layer, and still you don't. When these two hosts talk to each other, they don't see the things underlying. They don't see the things underlying the network. They don't. The only thing they see is the peers. Okay, this host will see this guy, and this will see this guy. So it is quite similar to the link layer protocol. So in a sense, that transport layer is quite similar to the link layer in the way they need to, in the issue they need to handle. For example, they need to handle the error control issue. They need to handle the flow control issue. They need to handle the addressing issue. So they face the same issues, but the characteristic of the issues are quite different. In the link layer, it's only they are immediate neighbors connected by just one link. So the delay distribution is quite fixed. So you will see that in the link layer, you run window-based. For example, you run window-based flow control. But in the transport layer, you also run the window-based flow control. But here, the window size will be fixed in the link layer. In the link layer, the window size will be fixed, usually because of what? The delay is quite fixed. So the window size will be fixed. However, in the transport layer, if you run the window-based flow control, the window size needs to be dynamic. Otherwise, you got problem because the delay distribution is quite loose. Okay, so so considering their similarity but also differences between the link layer and the transport layer, you see the solution will be different. And talk about addressing here. Here the addressing is only either the MAC address, the hardware address. Okay, but here the addressing is by, it's not enough on the host, what you have is that you have IP address, MAC address, and then TCP, the transport layer protocol. On top, there could be some programs running, which are called processes. When a program is run, it's called process. And the process needs to have its own address. The process needs to have its own address. And some process might have multiple address. Multiple address. For example, I want to occupy port 80. I also want to occupy port 23. Then I would have two addresses. Okay, and the address used by those processes are called port number. They are called port number. So for this program, it could be worldwide addressable by an IP address plus a port number. Okay, so I can address a process which is running somewhere on a machine. I can address that particular process by an IP address concatenated by a port number. Then I'll be able to talk to that process. With this address, IP address plus port number, I can address that particular process worldwide. So they could be worldwide addressable. So that's the reason why we need to provide port number at a transport layer. So you will see that TCP and UDP, these two transport protocol, they both have the port number, which is 16-bit port number that is used to address the process. So the addressing, and for error control, we have talked about that in chapter 1 and also chapter 3. For error control, if you, with the end-to-end argument, we understand that the link layer error control cannot solve the problem ultimately. The problem can only be solved ultimately at end-to-end, right? It's an end-to-end issue. It's an end-to-end argument. So it needs to be solved at the end-to-end layer. That is a transport layer. However, so in a sense, we don't need to handle error control at the link layer. But most link layers still embed some error control mechanism, and that's just for the purpose of efficiency. In efficiency in terms of earlier recovery of the error, earlier detection or recovery of the error. Okay, so we don't need to do that, but if we don't do that, the error will be detected and corrected much later at the transport layer. So we still want to do error control at the link layer so that the error can be detected and corrected much earlier before they propagate to the transport layer. That's for error control. So you will see the error control issue at the transport layer is they would use the similar mechanism. However, they use checksum. In the link layer, it uses CRC mostly for error detection, but in transport layer they use a checksum. We have discussed why. Let me ask you why again. Why are we using CRC at the link layer instead of checksum? Yeah, because CRC is easy to implement in hardware, and CRC provide better, can detect multiple errors, while checksum can only detect single error or one error or three error. But if you have even number error, you might get the correct checksum, even if you have 2 errors. Okay, so so in the transport layer, because the transport layer are mostly implemented in software, so we don't want to do CRC, we do checksum. So that's the error control. How about flow control? I just mentioned that for this kind of dense delay distribution, the link layer window control would use a fixed window. They would use fixed window. Okay, but in the transport layer, you would use a dynamic window. The window can grow or shrink. Okay, but we see in the link layer in the PPP, they don't HDLC use window-based flow control, but PPP does not. It would simplify into stop and wait flow control. Okay. So if you compare them, here it's summarized what some of the things I said. Okay, the link layer and transport layer, end-to-end layer, and addressing is by MAC address. Here addressing is by port number. And the error checking is you need to check you check frame. Here you check segment. So at a link layer we call it frame. At an IP layer we call packet. But here transport layer we call segment. We call it segment. Segment, packet, and frame. And the data reliability, it only guarantee it's correct on the link. But here you need to guarantee it's per flow. On the entire flow it's correct. And same for flow control. You control just the link, but here you control the flow. Here's an example. For example, Ethernet, if you have collision, the collision will be detected and then frame will be retransmitted. But if you have CRC error or alignment error, but no collision, in Ethernet it does not correct the error. You find in Ethernet if the CRC CRC check is incorrect, then it would drop the frame. No retransmission will be done. Okay, and it's left up to the upper layer. So in a sense, it does error control, but only does detection, but no correction for Ethernet. But on the transport layer, you would see that we need to do detection as well as correction, because that's the last line. The final defense line for error control is the transport layer. So you need to do that. You need to detect and correct. Okay, in the link layer, you might just do detect but no correction. But here you need to do detect and correct. If you need error control, if you need to guarantee it's correct. But however, you will see that UDP and TCP are quite different. In UDP, it's unreliable. It means that it does not correct the error. You will see that UDP does only detection, but no correction, no retransmission. But TCP does detection and correction, so it would do retransmission. Okay, that ends the discussion on general issues. to resolve. And the first open source implementation is the code graph, two code graph. One is the outgoing and one is incoming. So let's look at the incoming flow first. So here's the IP layer, and here's a transport layer, and then there is application layer. And when at the network layer, the IP layer, there's a function called IO local deliver finish. This function will call the transport layer entry function, and there are three protocols at the transport layer: the row, UDP, and TCP. The row means that no transport layer, just the direct access to the application, the IP layer, direct access to the IP layer. So no transport layer, no transport protocol here. Then you call this function, and then all the way up. If it's UDP, in the IP header, there's a field called protocol ID in the IP header, and that ID, that number, will tell which function you should call. Your payload, the payload in the IP packet, whether it's TCP or UDP or row. So from that number, you will know which function to call. And then once you call it, it goes all the way up. It continue to call, and then here at the end, this function will put the packet in the SK buff. That's the SK buff. You put the SK buff into a queue, this SK receive queue. So you put the packet into the queue, and then waiting here for the for the application program to access. So you will see it would look weird to you because the incoming flow, the incoming packet, here it's going up, but here it's calling down. It's calling up, but it's calling down here. That's because this is driven by the kernel. I mean the IP layer, but this is driven by the application layer. So why this will be called? That's because the application call a system call. If the application call a system call read or receive from, if it call read or receive from, it will call this function, and then eventually it will take it will copy the packet in the queue. This is a kernel within the kernel. Copy the packet here into the user space. So here, eventually, copy the packet from the kernel queue into the user space, into the space specified in the application program. So going down is driven by the application program, either the client or the server program. So, and because they call the system call, they call a system call, so it's calling down, and then they want to grab the data within the kernel queue and copy it into the user space. So they are actually packet copy from here to the user space. And once the copy is finished, the system call read or receive from will be returned. Okay. So when you call read in the socket programming, in programming a client or a server, you call read, it will block. Okay. And eventually it will return. When it returns, it means that the data you need, the data you want to read has been in your what? In your user space data structure that you specify in the read system call or receive from system call. you specify a variable that you want to read the data into that variable, and when it returns, when this function returns, when this system call returns, it'll be there. The data is ready there because it has been copied. And calling that system code actually triggers a sequence of code and eventually copy the data to the user space variable. Okay, that's incoming. How about outgoing? So what happens is that if there are data coming in, it will be queued here. Why do you need a queue? Because the application might not need it now. Even though there are incoming data, the application might not need it right away. So you need to have a space to queue the data, queue the incoming packet. Okay, you can't push the data to the application space, the user space. No, you can't. You need to put it in a queue, waiting for the application to grab. You can push. You can say, okay, I want to change the implementation by coding all the way up. No, if the application does not need the data should not be in the user space. It should be kept in the kernel space. But of course, there are some situation that you code. Suppose there are no data in the queue, but you call the read. So it will in turn call this, and then block waiting here because no data available. The queue is empty. So again, your read system code will not return because no data can be read. So your read system code will block, waiting for the data to become available. Okay. So either you have data coming in the kernel, your packet coming in the kernel, but the application program does not need it now, then you need a space to queue. Or you want to read, the application wants to read, but no data available, then the system code will be blocked, waiting for the data to come in. And once the data comes into the queue, the system code can be finished. And once it's finished, the data has been copied, and then the read system code will be returned. How about outgoing? Again, you separate, you still have a queue here. Okay, this is driven by the kernel. You can say that this is driven by the kernel, initiated by the kernel. But here, it is driven or initiated by the application program. So you still need a queue to store the packet. If the application writes a lot of packets, but the kernel cannot handle it as fast, then you need a queue. Okay, so once the application program has something to write or send to, it calls the system call, and then in turn it calls a sequence of kernel function, and eventually put the packet into the queue. And then I return. So then the write or send to system call will return. So when the write system call return, it means what? The data has been successfully passed to the kernel. But it doesn't mean the kernel has successfully transmitted the packet. No. It might not get transmitted yet. It only means that it's in the kernel. I have passed to the kernel, and now it's the kernel's job. So, so once I finish this, I'm done, and I return. Okay. So that's and you need this because the application might write a lot, and the kernel or the interface card cannot handle as fast. Okay. Pardon me? Yeah. See, on this graph and the other graph, incoming packet, you all have two system code. On the right-hand side, the system code is used for TCP socket, while on the left-hand side, it's used for UDP socket. And the difference is because on the TCP socket, it's connection-oriented. The socket can be used only for a pair, a particular peer, between me and the peer. And that's the socket. If I have another peer to talk with, I need to create another socket. And that's called connection-oriented. But on UDP, you will see that we create a socket. I can use the socket to talk with this guy and talk with that guy or talk with the other guy. And that's called connectionless. So I can use the same socket to talk with different people. That's called UDP socket. And so the parameter will be different. So with UDP socket, if you call receive from or send to, the system call receive from or send to, you need to specify who you are talking with. You need to specify, so the parameter will be different. But with read and write system call, because you have bind the socket with this guy, so you don't need to specify who you are talking with. The kernel knows that. The kernel knows that already, because that system call is connection oriented. Anyway, that socket is connection oriented and it's binded, and no need to specify the peer. But with the receive from and send to, you need to specify, so that the kernel knows who you will talk to. So the parameter will be different for these two system call. Okay, so is it clear why we have queues here and here? And why we have two different directions? I mean, one going up, one going down. And why here it's all going down? That's because the upper part is application driven, while the lower part is kernel driven.